Hi, I'm Artem. Yeah, I'm here to talk to you about Wunsafe-buffer-usage. And this is a newish warning that we're in the middle of implementing. And hopefully it eventually, ultimately, leads to bounce safe C++. And yeah, we're working on it. We are a team of 5. Jan is our manager, and everyone else is actually implementing it. And we're really proud of what we've built so far, and I'm gonna tell you about that. But first thing first, right? So the problem, right? The problem is buffer overflows and buffer overflows. We knew about them since the 90s. They continue to be a problem to this day. And we still have security critical software written in C++. And when major languages, right, when modern safe languages have eliminated this problem with a very simple approach, right? They perform a runtime check, right? You access into a buffer, the program performs a runtime check that the index is within the bounds of the buffer. Right, but in C++, this approach doesn't work because C++ and of course C as well has pointers, right? And pointers are a pointer is just an address. It doesn't know how much data does it point to. So even if we wanted to perform a runtime check, we wouldn't have enough information, and that's what makes this problem hard. But things are improving, and literally a few hours ago, you've seen a talk by Louis, our colleague, introducing Hardened libc. What does it do, right? It takes your favorite standard containers, span, array, vector, and it inserts runtime checks in the implementation of these containers. So when you index into a container, the indexing operator checks at runtime that the index is within bounds, just like in other modern safe languages. But that's not sufficient, right? If you continue to use these containers, you're safe, but you need to actually use them, right? And if the code continues to use raw pointers, if the code continues to be written as if it's C code, then transforming code to use safe containers, even when they're actually safe, it is an overwhelming amount of work. So there's room for compiler to step in here and make our lives a bit easier. So this is where our warning comes in, right? So we have this warning, Wunsafe-buffer-usage, right? What does it do? It identifies code that cannot be hardened through runtime checks because it doesn't have enough information, because it uses raw pointers primarily, right? And that's already pretty good. It's better than identifying this code by hand. But this isn't the actual novel part. So the actual novel part, the actual fun part, is that we provide FixIt. Right, so Wunsafe-buffer-usage comes with FixIts that take your code that uses raw pointers and transforms this code to use standard containers, so that later, when you enable libc++ hardening, they could be hardened, and this is how your program actually becomes safe. So let me give you a few examples how this is supposed to work, right? So there's some code, and there's actually a lot of code, but that's why we're here, right? We don't want to understand this code, we just want to convert it. All right, so how do we do this? First of all, enable libc++ hardening so that we could have some runtime checks to look forward to, then enable our warning, and then separately enable FixIts when you're ready for them, because they're amazing. Yeah, and back to our example, what this is going to do is it's going to show you a warning. Hey, this variable boof, it's a plain C array. It's not going to perform bounce checks for you. And the warning is accompanied by notes saying where exactly you're not going to have bounce checks. And these are unsafe operations, and these are the operations that tell us that boof deserves hardening, right? Specifically, even if you know the size of the buffer at compile time, you don't necessarily know the index at compile time, right? And finally, the compiler emits a suggestion. Hey, there's a standard container std array. Does this thing work? All right. Std array that, if library hardening is enabled, it's going to have a runtime check. And the last note has a FixIt, right? If you see this note in an IDE, it's going to have like a fix button that you can press, and the code is going to be transformed. So this is how transformed code is going to look like. In this case, everything is easy, right? We just changed a C array with a bounce checked array, but this is not the only thing that changed about the code, right? Right? Yeah, you have this array here that was explicit, that we needed to explicit write, but what you got automatically for free, in terms of source code changes, is the index operator is now replaced with the overloaded operator provided by std array that in libc++ hardened mode is going to be hardened. So this is how the program becomes bounce safe, right? So here's a different example. In this different example, you receive a buffer from elsewhere, and you don't really know who allocates or who controls this buffer. Once again, you receive the warning that obj is an unsafe pointer, and this is where people perform pointer arithmetic on it, which cannot be hardened, right? So. But in this case, the recommended replacement type is span, and span is not a container; it's a view, right? It's a view into someone else's buffer. So when I press the fix button, here's what's going to happen. So you see that you're using span instead of a row pointer. And here's something interesting. This is the IDE placeholder. So this is what the compiler does when it wants the user to fill in the missing details in the FixIt, right? It's commonly used by code completion when you code complete a function and you can write in some arguments, right? It's not commonly used by compilers, but this seems appropriate, right? So the missing bounds information, this is where it is, right? We in some cases we could discover it with the help of the compiler, but that's not the point, right? The point is that we automate everything else, and user can specify the intended bounds information this way, and that's an acceptable form of user interaction for us. And here's another tiny thing that you may notice. So originally the code was star ops plus I, and we changed it to ops of I. And so the reason why we had to change it is because ops became a span, and span is not a perfect drop-in replacement for a pointer. In particular, it doesn't support operation plus. It only supports subscripting, right? But at the same time, the updated code looks even better, right? And this is actually the thing that makes our tool good. We not only replace the types, but we also fit them back into code and consider all the possible places in which the code can break, and make these tiny corrections all over the place so that the code continues to compile. All right. So, okay. So. I wanted, I guess, talk more about the FixIt and how they're implemented, because These are this is like the actual novel part, and this is what makes the solution practical, right? And in order to talk about that, I need to talk a bit more about the requirements and the promises that we make to our users. And I guess the goal is obvious, right? We want runtime checks for bounds. And in order to perform runtime checks, what we really need is the bounds information, right? And like not only we want some bounds information, we want correct bounds information. And that's the most straightforward way to achieve it is to use standard containers such as span all the way, right? All the way. That's kind of the most interesting part, right? You want to like allocate a buffer, then immediately, like if you need to pass it elsewhere, you immediately put it into a span and then copy that span. You don't reconstruct it from raw parts, right? And yeah, and requirement number 3 is that we want transformations to be performed incrementally, right? Because that's how software is developed, right? Nobody likes large patches. Everybody likes small patches. And we're building our tool to accommodate that and to work correctly when the code is transformed partially. So, right. So we have a few negative requirements, right? There are things we don't want the tool to do. And the number 1 requirement is we'd rather avoid introducing compilation errors, right? We accept that sometimes placeholders are inevitable when there is not enough information in the program. But every time we introduce a compilation error, it increases the cost of transformation, right? The amount of time the engineer has to spend on updating the program. So this goes against our goals, right? Similarly, we don't want to break the program, right? Even if it compiles it, but if it suddenly starts behaving badly, that's really bad for us, and that's even harder. It wastes even more time. And requirement number 3, we don't want to transform code that does not deal with buffers. That's, I guess, the main part, right? We don't want to transform all pointers. We only want to transform the ones that point to buffers that are used for buffer operations. And we have to do clever things in order to satisfy this requirement. And requirement number 4 is, that's a really fun one. Transformations should actually converge, right? So because, well, I wouldn't have time to tell this story, but we had very funny examples where like the tool was producing code indefinitely, and we had to work our way we had to work hard to make sure that this doesn't happen. Right, and there's also this tiny requirement that transformed code would be idiomatic C++, right? And we'll talk about that in a moment. But idiomatic, right, it's not necessarily our goal. Our goal is to make it secure at low cost, right? And if we also make it idiomatic, that's great. But if we don't, it's probably okay. It's still worth it. Yeah. So this is how we see it. And what does this mean in practice, right? So correctness is kind of straightforward. What about incremental adoption, right? This is interesting. So it's easy to enable the warning file by file, and you often want to do that just start converting code gradually. That's okay. And by the way, libc hardening can also be enabled gradually on file by file basis, and sometimes this comes in handy, right? We also have we also provide a pragma that allows you to adopt the warning line by line. Right, that's a very small grain. Like you can surround your entire file in the pragma and then gradually shrink the pragma as you convert more and more code. Right, but the interesting part is what happens at the surface area between the code that adopts the warning and the code that doesn't. And here's a tiny example, right? The function receives a buffer, does something with it. And suppose we recommend a FixIt the function now accepts a span. Yeah, well, great, but what if there was a call site, right? So if there was a call site, then after this fix, the call site starts producing an error because you cannot stuff a row pointer in here. And this is exactly what we wanted. We don't want the row pointer to be there, but this is not incremental, right? This is like you're breaking everything. So in the spirit of incremental development, the FixIt is actually going to be looking more like this. There's a new compatibility overload that accepts the old parameters, and it like constructs the span from raw parts when necessary, so that to satisfy the call site requirement, right? So the FixIt generates this entire new function, and because of that, there's no more issues at the call site. Great, but do we actually like it that there are no more issues at the call site? We actually don't like it, because we still want to convert the call site to use the new safe function, right? That's what we came here for, and like we don't want people to use the compatibility overload. So it's just a temporary solution, right? Ideally, sometimes it's permanent, but like all temporary things. Yeah, but in order to encourage people not to use the new function, what the FixIt actually does is put a new compiler attribute on it that we've implemented for this purpose to mark it as undesirable for bounce safety, right? And once we have this attribute, then every call site starts emitting a Wunsafe-buffer-usage warning, which helps people convert all the call sites. And this is how the warning propagates from one function to another this way. Great. Yeah, now another requirement I talked about is that we don't want to transform code unnecessarily. And the problem with that is pointers, like not all pointers are created equal, right? And as C++ programmers, we're like it's like this meme, right? We're used for all these flavors of pointers, but the code that we're trying to convert typically looks like this. Right, and we have to deal with the code on the right, and we probably don't need to categorize that flavorfully, but we want to make sure that we don't, at least we discriminate between buffers and non-buffers, right? That's the really important part. Right, so there's certain static analysis that we've implemented to discover the role that every pointer plays, depending on how it's used, how the use patterns, right, and how it's declared sometimes. And for every buffer pointer that we discovered this way, and not for any other pointer discovered this way, we suggest replacement types. And the way this analysis works, it's a simple analysis. It basically tries to detect individual patterns, right? We call them gadgets, right? They're like crop gadgets or something, because they not necessarily unsafe, but the final solution is built as a combination of them, right? So here's some clear example. Again, you don't have to understand what's going on. The tool doesn't understand it either, right? But the tool sees these tiny patterns, right? So these tiny patterns are obvious, right? They're arithmetic. They tell us that Q and R are row pointers that point to some buffer, right? These operations wouldn't make sense if it wasn't a buffer, right? Now these two tiny gadgets are interesting because they don't tell us that something is a buffer specifically, but they tell us that P, Q, and R are actually kind of the same object, right? Which happens to be a buffer because R is a buffer and Q is a buffer. Therefore, P is also the buffer, and moreover, P is actually where all the bounds information comes from, right? As through the parameter. So if we want to transform Q and R, we probably also want to transform the parameter P, right? And there are other gadgets of this nature. Like what about this one, right? It tells us that P is actually nullable. Can we use like some like nullable type here, right? There's some comparisons, right? What about return type? Do we want to transform that as well? So basically, our tool treats these requirements as a system of equations. And we're trying really hard not to try real hard to solve it, but there are some fancy algorithms that we've implemented already. Right. And finally, when we try not to break the code, the idea is roughly the same, right? So we need to inspect every use of the variable. Otherwise, we don't know that we don't need to fix every use. And we need to confirm that type and value kind doesn't change because type checker will be unhappy otherwise, right? We need to confirm that runtime traps makes sense at every use. And this brings a lot of attention to the context of every use. And what we do is we classify these different contexts, which are also basically the same gadget pattern, right? And this is the most time-consuming aspect of our work. That's why we are working so hard on it. And we've implemented like a few dozen gadgets. There are a few dozen more that we want to implement. And by the way, you can join, you can catch us that, hey, you didn't implement this gadget yet. I'd like to contribute. We're happy to work with, but this doesn't mean that we're stopped working on it. We continue to work on it. Yeah, so this is how it's going. Right, so long story short, yay, we have the new hardened mode, and we implemented compiler warning that covers that helps you deal with code that does not use the hardened containers yet. And this warning comes with FixIts. We're like actively developing them, but we implemented some cool architecture, and we're really proud of it. And documentation coming soon. I wanted to commit it before the conference, but didn't have time. But like, if you check it like in a week, hopefully it's going to be there. But again, something may come up. Okay, so this is what I wanted to talk about. So thank you for listening. I'm like.
So my question is about how does that interact with templates, right? Like template definition, like when doing semantic analysis, you may not like be able to figure out that like you're dealing with pointers at that time, right? You might have like dependent times. So like how is that working?
So we have not touched that part that deeply yet. So this is like definitely like a not implemented part. And what do we mean by not implemented? We mean that you're going to continue to receive warnings about unsafe operations, right? And in case of templates, Clang naturally deals with them by because like in Clang AST, templates are like copy pasted for every instantiation, right? So we analyze instantiations. Right, but implementing like good high quality fixits is probably going to be challenging, and yeah. So basically, when something is not implemented, this means that you have a warning but it doesn't come with a fixit yet, right? So hopefully we will cover the most common examples, right? Where like our right, we don't have to cover everything, right? We cover, like even if we cover like 90% of cases, it's still going to be like tremendously helpful to developers converting their code. And if they have to change a couple places manually, that's probably okay. That's still better, right? So maybe we will have to implement this behavior in a couple of cases.
All right, thank you.
As an offer of a new warning, how do you feel about projects that enable WAll, WExtra, WError by default?
We have a complicated relationship with these projects. So the warning is off by default. It's not in WAll, but it is in W everything because everything is in W everything because it's literally everything. So we've got a couple people running into this warning and having problems with it because we were like in the middle of implementing it. So for now, we just talked to them and told them that, hey, this is what the warning is doing, and it kind of makes sense for the warning, but it doesn't necessarily make sense for you. So you have to. So I think this is already the case in W everything that like most people don't actually want W everything, but a lot of people feel okay with W everything and a few warnings disabled that they really don't want to satisfy. So I think our warning just falls into that category for people who don't actually want to satisfy it and just run into it accidentally.
So do you already have any data on how many of those fixits can be applied automatically and work without user intervention, and for how many cases the user actually needs to, like do some changes, like you said, you introduce some placeholder and then the user needs to fill it in?
So let's see. So like we're like still implementing it, right? And we're feeling okay with infrastructure, but before we fill in all the gadgets, it's still right. So I think for now the number is like relatively low. I don't know, like what is like 10% maybe. So that's definitely not sufficient for us. We'll continue to work until we get like a reasonable number, right? And if like we probably cannot stop at 50%, right? 50% means bound safety is like twice as easy to adopt, which like twice as easy to achieve, but that's nowhere near enough for these big projects, right? So we're aiming for a pretty high number, but we need to like pour the algorithm with some data.
Okay, thanks.
Before we get there. Mm-hmm.
Hi, I wanted to ask why did you pick to make a compatibility function instead of changing the call sites, because those are also available through the ASD Matchers API.
What do you mean? Like,
so for example, with the fsafe buffer suggestions, one of the slides created a compatibility function foo instead of going through the ASD and then finding the call sites for the function, and you could replace a certain argument.
Why don't we replace the call sites immediately, right?
Yes.
So a lot of this has to do with us living in the compiler, right? And the compiler compiles one translation unit at a time, right? So if the call site is in a different CPP file, that's not going to work, right? Like we cannot talk to the compiler of that CPP file to do the transformation for us. So we could do that within the current file, and maybe we should, but this will not eliminate the need to generate the overload.
I see. Is there a plan? Are there any plans to delete the generated code automatically, or would that need a by hand replacement? Because this, I understand that if it's across different translation units, you can't avoid having a placeholder function, but that also adds the extra step, and the problem becomes slightly harder now. Yeah, because you have to replace this function with another function.
It does make the problem like significantly harder, and that's in most cases we prefer to actually make multiple steps at once, right? So for example, in the PQR example, right here, right. We want to transform P, Q, and R in a single step. Otherwise, the problem becomes significantly harder, because suddenly you're dealing with a program that already has some bounds information, right, and already has some placeholders that the user have resolved. And now instead of proving that our transform program is equivalent to the original program that had no bounds information, we suddenly need to prove that it's equivalent to this partially transformed program and we have already forgotten which parts mattered and which parts didn't matter in the original code. So this is why we actually prefer to transform multiple things at a time, and that's like an important insight that we've gathered. But yeah, so if we have like the infrastructure at like and there are a lot of people in the compiler who want this infrastructure. Like LTO is kind of that kind of infrastructure, right? That like connects multiple translation units together, right? So it's definitely a dream for us to eventually converge to like a push button solution where you just push a button and the entire program, or the entire project transforms, and that would actually be better for the users and also better for us for like correctness and for like this like compatibility overloads. This like transformation boundary definitely takes it all, right? But yeah, but like it's pretty likely that we still need to deal with that boundary, right? If like the project is a library and like you don't want to break all the users of your library by switching to a safe interface. Maybe some of your users don't even use C++, right? So we still need this. So we started with this that we need anyway. We definitely need it, and it gives us an answer in all cases.
Thank you.
We have one last question. Sorry. Probably you can avoid wrappers if the function is static, or in
yes.
anonymous namespace,
Yes.
or it is private to
Yes,
the class.
yes. If the function is not externally visible and it does not like escape by pointer, and we can actually confirm it in the compiler. So like then in this case we can avoid the overload.
So is transforming for into for each loop in some simple cases as in scope of this project or out of scope?
So it's like a little bit out of scope, right? We want transformed code to be idiomatic, right? But we don't want it very hard, right? It's more important for us to provide a cheap push button solution for security, like from security perspective, right? And maybe there could be like a separate modernizer simplifier tool that, for example, converts iterator-based loop to a like range-based loop. And I think Clang already comes with some of these. But we could implement some of these cases, right? And we did implement the square bracket case, right? Which one is this? Yeah, this one, right? Because in this case, it not only is idiomatic, but it also unblocks our progress in a nice way.
Thank you.
Thank the speaker.